Okay. We're on. All right. Are there any questions? Okay. The last thing we were talking about was Burke's output theorem that says that in a MMSQ in equilibrium, the output process is a Poisson process. And I said that there was another way to prove that using an argument called reversibility. And that turns out to be a very interesting way of looking at things. And so I thought I would go through that. So to begin with, I have to step back a bit and do some stuff that we hadn't done before, regular probability. So I'm looking back on page 48. And the first thing is I want to recognize that what I'm going to talk about here is the case where I've got two random variables, x1 and x2, let's say. And they're, in a sense, racing against each other. And as we've already discussed in class, I'm going to assume that x1 is exponential with rate lambda 1, and x2 is exponential with rate lambda 2. And x1 and x2 are independent. So one thing we've already discussed is that suppose I wanted to find the distribution of the min. In other words, the question is, what's the probability that the smaller, the min of x1 and x2 is greater than t? Now, the only way that the min can be greater than t means that they must both be greater than t. So by ordinary logic, that probability is the same as this probability. But by the assumption of independence, okay, so if here I'm going to assume independence, then the probability of the marginal distribution factors into the product of the, the probability of joint distribution factors into the product of the marginals. So this becomes the probability that x1 is greater than t times the probability that x2 is greater than t. And then because these are assumed to be exponential, that first probability is e to the minus lambda 1t. The second one is e to the minus lambda 2t. And then by arithmetic, that's the same as e to the minus lambda 1 plus lambda 2t. And so what we see then is that if we have exponentially distributed independent random variables, then the probability that the smallest one is greater than t is also exponentially distributed with a rate equal to the sum of the original rates. Okay, so that's a fact that I'm going to use in a moment. Now, the question I want to ask is actually given by exercise 15 on page 49. Okay, so we're on exercise 15, page 49. And there the question is to find the distribution of the min given the condition that you know which one the min is. So I want to calculate the probability that the min is greater than t. Given that I know that, let's see, to do it in the same terms as in the example, in the exercise, given that x1 is less than x2. Okay, first let me ask, because I don't remember, have I discussed this problem in class? I don't think so. Okay. If I have, you don't remember. So either way, it's okay to discuss it. Okay, so here's the question. I have these two random variables racing against each other. And what they do is they form an interval. The interval is the length of the shorter one. And then I say to you, now, what's the probability that that length is a certain amount if I know which random variable ran the race? In other words, I have two runners running against each other, and the race lasts as long as the faster runner. And the question is, okay, now, suppose I tell you who wins the race. What information does that give me about how long the race took? You could argue that, well, if I told you that the faster runner ran the race, suppose I tell you the slower runner is the winner of the race. Okay? Now, if the slower runner is the winner of the race, what does that mean about the length of the race? One argument is, well, if the slower runner won the race, he must have really run fast. And the other argument is, if the slower runner won the race, then the faster runner must really have run slow. So what does that mean about the length of the race? Is it faster or shorter? Well, it depends. So now what I want to do is I want to calculate this probability. Okay, so that's equal to, this is a conditional probability. So the denominator is the probability of the event on which I'm conditioning, and the numerator is the probability of the events jointly. So we want the probability that jointly the min is greater than t and x1 is less than x2. So now I'll calculate each of those separately. So let me do the denominator first. It's easier. So what I'll do is I'll let f1 be the distribution function of the random variable x1. So then df1 of u is the probability that x1 lasts exactly u, or lies in an infinitesimal interval about the point u. Remember that if, and we'll get into this shortly, if this distribution function is differentiable, meaning that the random variable has a density, then this would be the density function times du. And in fact, that's going to be the case here because we're talking about exponential variables. But in any event, in general, I could write it this way. So this is the probability that the first random variable, x1, takes a value u. So we want the probability to multiply that by then if x1 takes the value u, that x2 is greater than u. We want the probability that x2 is greater than x1. Okay, so that would be 1 minus the distribution function of the second random variable evaluated at u. Those things multiply because they're independent. And then I would integrate that over all values of u between 0 and infinity. These are non-negative random variables. Okay, everybody buy that? Let me go through that argument again. We want to calculate the probability that random variable 1 is less than random variable 2 when these are independent random variables. So I'll arbitrarily pick x1 as the one I'm going to fix. So I'll imagine that x1 takes a value u, which it does with this probability, and then I will multiply that by the probability that then x2 is greater than that value u, which it has with this probability, and then I will add those up over all possible values of u. So that will give me the probability then that x2 is greater than x1. Okay, just let me do that. So now I'm going to do it for the case in which the random variables x1 and x2 are assumed to be exponential. So that means that this piece here would be replaced by lambda 1 e to the minus lambda 1 u du. That's the density function for the exponential random variable times du. This is 1 minus the distribution function for the exponential random variable. So that would be e to the minus lambda 2 u. And then I would have to integrate this as u ranges from 0 to infinity. So now this is just a simple integration. But actually, this is easy integration to do because all I'll do is factor out the lambda 1 and then multiply, so this lambda 1 is outside, and then multiply and divide inside, multiply and divide by lambda 1 over lambda 1 plus lambda 2. So here I'll write lambda 1 plus lambda 2, and here I'll write lambda 1 plus lambda 2. The reason for doing that is to recognize that now what I have as the integrand is lambda 1 plus lambda 2 times e to the minus lambda 1 plus lambda 2 u du. So you see that what I have inside the integrand is actually a density function for an exponential random variable whose rate is lambda 1 plus lambda 2. So that means that that integral would work out to be 1. Okay, so this whole integral is 1. Of course, I didn't really have to go through this little trick. I could have simply integrated it. But this allows me to integrate it by recognizing things rather than by doing arithmetic. So the value of the integral is 1, which means that the denominator is lambda 1 over lambda 1 plus lambda 2. And in fact, this is a rather nice result. It says that if I have two exponential variables racing against each other, independent exponential variables racing against each other, then the probability that a particular one wins the race is the ratio of its rate to the sum of the rates. So I think that if you had to make a guess, the simplest possible reasonable thing that this answer could be, that would be the answer. Of course, that's characteristic of the exponential distribution. Everything always works out nicely. OK, now let's look at the numerator. The numerator, I want the joint probability that x1 is less than x2 and the min is greater than t. Well, now I'll just use the same reasoning for the numerator as for the denominator. I'll say, first of all, df1 of u. That's the probability that one of the variables takes the value u. Then I will multiply that by the probability that the other variable takes a value greater than u. So now I have this part here that says that x2 is greater than x1. But it must also be true that the min is greater than t. But x1, if x1 is to be less than x2, then to say the min must be greater than t is to say that x1 must be greater than t. So instead of integrating from 0 to infinity, as I did in the denominator, I'll integrate from t to infinity. OK, so let me go back over this argument. This is the probability that one of the random variables takes the value u. This is the probability the other one takes a value greater than u. And then by integrating from t to infinity, I add that up over all values such that the first one, which is the smaller one, is at least t. So then I will have met the condition that x1 will be less than x2 and the min will be greater than t. So now everything is the same. I have exactly the same kind of arithmetic as before, assuming, again, that the f's are exponential. So what that would give me is this. If I went through this arithmetic, I'll get my lambda 1 over lambda 1 plus lambda 2. That comes outside the integral sign. And inside, I have lambda 1 plus lambda 2 e to the minus lambda 1 plus lambda 2 u du, except that instead of going from 0 to infinity, I go from t to infinity. OK, now if I went from 0 to infinity, this integral would be 1. That's what I got in the denominator. But by the same argument, I can recognize, I can say, well, wait a minute. This is the density function of an exponential. And so if I took the density function and I integrated from t to infinity, that would be the probability that an exponential whose rate is lambda 1 plus lambda 2 takes a value greater than t. So I don't actually have to work out the integral. I know what it's going to be. The integral itself is going to turn out to be e to the minus lambda 1 plus lambda 2 t. That's the integral. The other part, lambda 1 over lambda 1 plus lambda 2, is the same. And of course, what you see is that the lambda 1 over lambda 1 plus lambda 2 cancels. And I'm left with e to the minus lambda 1 plus lambda 2 t. OK, but from that, I recognize, by looking at this, that that is exactly the same as the unconditional probability that the min is greater than t. Because that and that are the same thing. So that's really amazing, because what it says is that, well, we made the argument before that we didn't know whether or not knowledge of who won the race would tend to make the race longer or tend to make the race shorter. Well, if you don't know, there's always the possibility that it has no effect, that it neither makes it longer nor shorter. And of course, if there is any distribution which is going to have that property, it's going to be just in the middle, that's going to be the exponential distribution. Somehow or other, the Markov property of the exponential is coming into play here. And the end result is that this probability, this conditional probability, is the same as this unconditional probability. In this case, the result is interesting, and the method of analysis, of course, is worth knowing. OK, but what does that mean? If the probability of A given B is equal to the probability of A, then A and B are independent. So that means that if I have two exponential variables racing against each other, the length of the race and the winner of the race are independent of each other. If I tell you how long the race lasts, I don't give you any information about who won it. And if I tell you who won it, I don't give you any information about how long it lasts. That's true, of course, I proved it, if the random variables are exponential. If they're not exponential, then generally it's not going to happen. In fact, it will probably not happen at all. Probably exponential is the only one, because things aren't going to cancel out as nicely. All right, so this is the fact that I want to use now to go back and look at output processes from MMSQ. OK on this? Of course, this is in the book. This is exercise number 15 on page 49, and you have the solution worked out in the solutions manual. OK, so now let's go to the question of the output process. Yes, question.
It seems that if you only consider the minimum possible, the lowest one, it seems that if we divided the two cases, x1 smaller than x2 and x2 smaller than x1, it seems that this one should be the summation of that two parts, which means
no. OK, if I looked at both of them, the answer, in a sense, is 1. Either x1 is the winner or x2 is the winner. So I'm just arbitrarily choosing one of them and saying I have this race, and I know I observed who won the race, and I want to know what effect it has on the distribution of on the length of the race. And the answer is, well, if I tell you that x1 won the race, it doesn't tell me how long the race was. Therefore, if I had told you that x2 won the race, well, that wouldn't tell me how long the race is either. In other words, what I'm saying is that if I tell you that there's a race between two exponentials, then the identity of the winner of the race and the length of the race are independent of each other. OK? I want to know the probability that the race lasts longer than t if I tell you who won and who lost.
has nothing to do with this.
Which has not.
Independent.
What?
You mean the condition of x1 and x2 has nothing to do with the minimum.
Yeah,
That's right. That's what I'm proving.
Yeah.
That's the point. Because that's surprising, right?
It is surprising since intuitively these two parts added to the third one.
I'm not sure what you mean by
They say the p minimum x1, x2 larger than t, x1 less than x2 plus the same, but x2 less than x1.
I understand. Right.
Those summation gets the result.
That's right. But then it wouldn't. But then that wouldn't give you any information about independence, because somebody has to win the race. So just telling you that there was a winner, of course, doesn't tell you how long the race took. The important point is that if the runners have different rates and you say who is the winner, that still doesn't tell you how long the race took. The reason that happens is because when I plug in for the exponential at this step. Everything's okay in general at this step. When I plug in for the exponential, then everything cancels. And I'm left with something which I can identify as, from a separate calculation, the probability that the min is greater than t. So since the probability of this event given this is the same as the probability of this event without regard to this, that means that they are independent events. Now, it is surprising because I think that the only distribution for which it's true is the exponential. I'm not sure about that, but I wouldn't be surprised if this property characterizes the exponential. But it's certainly not true in general, because you just take an arbitrary f's, and put them in here, and you're going to get garbage. I mean, you're not going to get this cancellation here with this piece left right there. Okay, now this is important for our application, because now I want to go back to the model of an MMSQ and look at the output process. Okay, so can I erase this? Actually, from my point of view as a general entertainer, the best outcome of this lecture is that you're surprised, but you don't doubt my argument. If you're not surprised, then who cares? Then I could have said, well, it's obvious, we don't have to go through this argument. But if you're surprised and you think I made a mistake in the argument, well, then we've got to argue that part out. So you're surprised at the result, but you don't disagree with my argument. Is that correct?
I agree.
You agree with the result?
But it seems that intuitively, say the two parts added to the total. But the critical point is that the
right. So you are surprised, and you do agree with the result. Okay. I mean, there's no question I can answer, right? Since you're not arguing with my method, there's no problem there. And the surprising part, of course, that's just a matter of your previous intuition. There's nothing to argue about there at all. Okay, so this turns out to be the heart of the argument that we're going to make in a minute, which will prove Burke's theorem without doing any more arithmetic. And so it's a completely different proof than the one that Burke gave. In fact, this was the proof that was given by Reich. Okay, so let's draw a picture of an MMSQ. So here is the state of the system at time t, number at time t, and here's t running along here. So let's say the system starts at empty. Okay, so an arrival occurs, and you jump to state 1, and you stay in state 1 a while, and then maybe another arrival occurs, and then you jump to state 2, and you stay there a while, and let's say another arrival occurs, and you go to state 3, and maybe after a while in state 3 a departure occurs. And then maybe an arrival occurs, and then a departure, and then another departure, and another departure, and then sometime later an arrival, and so on, like that. Now, in fact, it doesn't have to be an MMSQ for this diagram to be descriptive. Actually, any queuing model, in fact, it doesn't have to be a queue, but in the context of queues, if I have arrivals and departures one at a time, and there's an infinite capacity so that every arrival results in a jump up, and every departure results in a jump down until I get to 0, then the state sample path, so to speak, that's what this is called, is a sample path. Then the sample path of this process looks something like that. So the only way you can tell one queue from another by looking at the sample path is in terms of the statistical properties of it, not the shape. Okay, now let's look at a particular level. Okay, so let's say that here's a level. So let's say I'm in level J. So I enter this level, I stay there a while, and then I leave it. Now, how long does that level last? Well, if it's MMS, MMS means that we have all the underlying distributions are exponential. We have Poisson arrivals, which means exponential inter-arrival times, and we have exponential service times. So when I'm in this state, then I have a race between the arrivals and the departures. So I'm going to stay in this state until either an arrival occurs, in which case I'm going to jump up, or a departure occurs, in which case I'm going to jump down. Now, how much time does it take until a departure occurs? Well, that depends on the state. But if I'm in level J, then we know that each customer, that means that there are J customers in progress. No, it doesn't necessarily. If I'm in level J, if J is more than S, there are S customers in progress. If J is less than S, there are J customers in progress. But in any event, the number of customers in progress, each of those customers has an exponential time. So the time until the first customer completes service is the minimum of those exponentials, and therefore that time is exponentially distributed with the rate equal to the sum of the rates. So if mu of J is the service completion rate, the aggregate service completion rate, this is the way we defined it. We said mu of J is equal to J mu if J is less than S, and it's equal to S mu if J is greater than or equal to S. In any event, depending on the state, the time until the next departure occurs is exponentially distributed with parameter mu of J. So it's an exponential variable. Okay, now similarly, what about the arrivals? Well, the arrivals, the time to the next arrival is exponentially distributed with rate lambda by assumption of Poisson input. So that means that at the start of when I enter this level, because of the Markov property, nothing matters except the value of the level. That is, how many customers are present. But the length of time since the last arrival and the lengths of service of the customers present is irrelevant because all the distributions are exponential. From this point until the next event, which is either an arrival or departure, that is going to be distributed as the min of these two random variables, x1 and x2, where x1, let's say, represents the time until the next arrival, and x2 represents the time until the next departure. So in other words, this thing is distributed as an exponential, and its rate is lambda plus mu of J, the sum of the arrival rate and the departure rate. Okay, so each of these intervals then is exponentially distributed. Now, they're all exponentially distributed. And from the theorem that we just proved here, if I told you at the end of the interval whether the interval ended by a jump up or the interval ended by a jump down, that wouldn't give you any information about how long the interval lasts. So the length of the interval is exponential and depends only on its level and not on whether it started from an up or a down or whether it ended with an up and a down. Okay, now comes the key insight. Well, maybe that was the key insight. There's sort of two things being combined here. Suppose now that instead of looking at the process where time runs from left to right, suppose I assume it ran from right to left. In other words, I'm going to imagine that I'm going to look at the same process. Let's say that this is being generated. I have a sample path for a particular Q, and I've got this sequence of these diagrams, these boxes. And now I'm going to take the same thing, and I'm going to run it by you, except that instead of having it unfold by looking this way, I'm going to have it unfold by taking the diagram and looking at it backwards. So in effect, I'm going to interchange every departure for an arrival and every arrival for a departure. And the question is, could I tell the difference? If I looked at this diagram going backwards, could I tell that, that it's going backwards or not? Or is it statistically the same thing? OK, now I claim that you couldn't tell the difference. Because how could I ever tell the difference in any case? Well, if I took any Q and ran its diagram backwards, I would have exactly the same lengths of the intervals, because it's the same diagram. And I would have exactly the same fraction of jumps up and jumps down from each state, because it's the same diagram. The only thing that could change would be the shape of the diagram in the following sense. Let me give an example where I could tell a difference. Suppose that the diagram looked like this, just to exaggerate a little bit. Suppose that every time I jumped up, or that every time I had a long interval, I tend to jump up. And every time I have a short interval, I tend to jump down. Like that, for example. Now, of course, I have the same number of ups and downs as long as I reach the same states. If I were to run this diagram backwards, though, you would immediately know it's backwards, because what you'd be seeing is a bunch of short ones followed by a bunch of long ones, as opposed to running it in the other direction, where I'd see a bunch of long ones followed by a bunch of short ones. In other words, if there was a relationship between the length of the time I spent in the state and the direction that I jumped when the state ended, then by running the thing backwards, I could spot that. Maybe it would be difficult, but in principle, statistically, it would be different. I'd have a different pattern looking from right to left than I would have looking from left to right. The only time I would have the same pattern from a statistical point of view is if, when I got to the end of the interval, jumping up or jumping down was not affected by how long the interval is. If the length of the interval is independent of what happens at the end of the interval, then I can't tell the two diagrams apart. In the case in which the length of the interval is exponential and is determined by who wins this race, I can't tell the difference, because that's what I just proved here. So therefore, the claim is that if this is an MMSQ, which then would produce exponential intervals in which the end of the interval would simply be the winner of the race, because by the end of a race between arrivals and departures, then if I ran this same diagram backwards or forwards, statistically I couldn't tell which was which. OK, so statistically, the diagram running backwards is the same as the diagram running forwards, then the statistical properties of the departures must be the same as the statistical properties of the arrivals. In other words, if the times between arrivals are IID exponential, then the times between departures must also be IID exponential. But the times between arrivals are IID exponential by assumption, because we have Poisson input. And therefore, the departures must constitute a Poisson process. So if I have Poisson input, then I must have Poisson output. Now, it's interesting, it's also true in Burke's proof, that it doesn't matter what the form of this thing is. In our case, that's what the mu's are. But actually, all that matters is that the total time spent here is exponential, and that it doesn't make any difference what this mu j is, as long as this mu j is an exponential, and at the end of that exponential, the length of the exponential has no bearing on whether, when the interval ended, it decided to jump up or decided to jump down. So the assumption that we have exponential surface times with these rates, j mu when j is less than s and s mu when j is greater than or equal to s, that's not critical. And in fact, it can be shown that this property of reversibility this is true for any birth and death process. Okay, any Berthon, because that doesn't necessarily mean that that I have a Poisson output process, because not every birth and death process is Poisson input. But any birth and death process has the property that, statistically speaking, I can't tell the difference from looking at it left to right or right to left. And in particular, if it's a if that birth and death process represents a state of an Erlang delay queue, then the output process is a Poisson process. This is discussed, if you want a readable, low-level description of it, in the book by Ross. Ross has about 5 or 7 or 8 books on probability, stochastic processes, and things like that. But there's one book called, gee, what is the name of that one book? Probability Models, I believe. It's sort of an intermediate level book that kind of bridges the gap between ordinary elementary probability and stochastic processes. And in fact, I'm teaching a course which is called something like Probability Models for Engineers, or Engineering, or something like that, which is a 5,000 level master's course in the manufacturing engineering program. And that course is supposed to be an intermediate course between undergraduate probability, which everybody's supposed to know but always claims they never took or forgot, and applications of probability in things like queuing theory. And in that course, I'll be using this book. So this book is around, it's available. So if you're interested in reversibility, I suggest that's a good place to start. Picked up this book, and it's listed under the term reversibility in the index. Okay, so that proves what I wanted to prove. Notice that the argument here is completely different from Burke's argument. It doesn't implicitly bring into play the pasta property. It doesn't require rate up equals rate down for the birth and death queue explicitly, and it doesn't require any statement about the departure, the state probabilities at departure epochs being the same as at arrival epochs. So Burke's, and there's no differential equation in here. So Burke's argument was very clever, and that, of course, it was the first. It was the original proof, and very insightful, although it seemed it was very special. This idea of reversibility is much more broadly applicable, much more general, and in fact is really simpler, at least intuitively simpler, because now it sort of makes sense to me why the output process should be a Poisson. With Burke's proof, all I could say is, well, if I follow each step and believe each step, then the conclusion must be correct, but I don't have any insight as to why that's true. Actually, that's kind of strange, because Burke's proofs, Burke's analyses are almost always based on insight. He had the most incredible insight into these probabilistic problems. And I guess his insight was there in this case because he must have known, that somehow or other he had to come up with an argument to prove that the output process was a Poisson process. If he didn't know that, he certainly never would have sat down and started doodling and just say, well, look at that, it comes out to be a Poisson process. But still, that proof is sort of now consigned, I think, to the literature. And if you're going to study, say, queuing networks now, the kinds of arguments people tend to use are these reversibility arguments. Okay, any questions about that? If not, let's go to the next topic, which starts on page 192. So now I want to do some of this mathematics stuff that's necessary, develop some of the tools, although of course I'm not going to do it in a rigorous fashion. I just want to state the facts. So I'm going to talk about Riemann-Stieltjes integrals. section 5.5. Riemann integration. And actually, Riemann-Stieltjes integration is a generalization of ordinary Riemann integration, the stuff you learn in freshman calculus. But to me, it's a lot easier. It's easier to understand the more general case and then specialize to ordinary calculus than it is to learn freshman calculus originally. So it seems to me anyhow. Okay, so here's the basic idea. Suppose I have a set of an interval, AB. And the interval is broken up into subintervals. And so I'll call these points here. So here is x0 is A, and x sub n is B. And someplace in the middle here, I've got x sub k minus 1 and x sub k. Let's see, is that the way I want to call it? Yeah. Okay, so I've got x sub k minus 1, x sub k, and in the middle of that, I've got some point zeta k. And what I'm going to do is I'm going to define the norm. That's delta with 2 bars around it, as the maximum value of these intervals. That has got a whole lot of intervals. And so if I take the max of x1 minus x0 and x2 minus x1 and so on, xn minus 1 minus xn, no, xn minus xn minus 1, that thing is called the norm. It's just the largest one of these intervals. Okay, now I'm going to define an integral in the following way. The integral from a to b of some function g of x with respect to some other function h of x. So this is g of x times the differential of h of x integrated from a to b. This is a definition now. Okay, definition. So what I'm going to define it as is this. I'm going to evaluate the function g at these intermediate points zeta. Okay, so that's this value here. I'm going to multiply the value of g by the difference between h as h goes from this part of the interval to that part of the interval. So that's going to be multiplied by h evaluated at x sub k minus h evaluated at x sub k minus 1. And then I'm going to sum that over all values of k as k goes from 1 to n. Okay, so what I'm doing is there's a zeta sub 1 here, and a zeta sub 2 here, zeta sub 3 here, and so forth. And so what this says is take g evaluated at the intermediate point and multiply it by the amount by which the function h changes between here and here. And then add in the value of g at this intermediate point and multiply that by the amount by which the function h changes from here to here and add those things up. And then, of course, take the limit of that as the delta, as the norm, goes to 0. So what I'm doing is I'm squeezing these points together so that if the largest interval goes to 0, then of course they all go to 0. And so what I'm doing is I am, in a sense, adding up an infinite number of these infinitesimal values, where each value is the value of g at some point times the amount by which h changes at that point. And then I just add those things up.
Which means n goes to infinity.
What's that?
Which means n goes to infinity.
Yes, n goes to infinity. Right. Okay, now, the point here is that just like with ordinary calculus, there are ways to calculate this integral that are easier than evaluating the definition. Okay, in particular, let's look at ordinary calculus. Okay. If h of x equals x, then get ordinary Riemann integral. Okay, if you go over here, and in this definition, I take the h of x to be not simply the value of some arbitrary function of h at this point and this point, but I take this h of x to be simply x, then of course h of x minus h of x of k minus h of x of k minus 1 is simply the length of that interval, or what in calculus you call delta x. So in the special case in which the function h is simply the length of the interval, it's simply the value of x, then you get the ordinary Riemann integral of calculus. Okay, now the fundamental theorem of calculus says this. Let me remind you. Here's the point. So we have the fundamental theorem of ordinary calculus. And the idea is that if I want to evaluate the integral from a to b of g of x dx, that's ordinary, the ordinary case, h of x equals x, then what I do is I find some other function, capital G, and I simply take capital G at b and capital G at a and subtract them. And the way I get capital G is this, where capital G of x is the function whose derivative is little g. That's truly an amazing theorem, although calculus students, freshmen, don't appreciate it. If you ask them what the fundamental theorem of calculus is, they can study calculus for years and haven't the faintest idea. Okay? But the idea is that if you take the particular case in which h of x equals x, then in effect, this limit here reduces to the area. It's the area under the curve. And the amazing thing is that if I want to calculate the area under the curve, of course, numerically, I could calculate this way and get as accurate as I want. But what the theorem says is that all I have to do is find some function g that has the property that the integrand is the derivative of that function. And if I can find that function g, then the value of the area is simply g evaluated here, big G, minus big G evaluated here. So I don't have to calculate the area by actually calculating this thing. The theorem says that I can calculate it this way. Now, when it's defined for freshmen, usually first thing they learn about integrals is the indefinite integral. An indefinite integral, by definition, is evaluated by finding the function whose derivative is the integrand. That's what you mean by indefinite integral. Go backwards. And then they tell you, OK, now let's take the area and let's call that the same thing as the indefinite integral between a and b, and then you evaluate it exactly the same way. Of course, the theorem is that the amazing thing is that the indefinite integral and the definite integral have anything to do with each other. I mean, of course, they do by their names, by words. But the point is that the indefinite integral is simply an inverse, and the definite integral is a specific limit that corresponds to an area. And the theorem says, believe it or not, those things are related. They're essentially equal. OK, now this just generalizes one step by taking the h to be arbitrary instead of h of x equals x. So when h of x equals x, then this thing is an area, and otherwise it's not an area. Generalized area, something like that. Okay, that's going to be important because when we do some work in queuing theory, we're going to want to evaluate things that look like this. Okay, so the first thing is that essentially all of the elementary properties of the ordinary Riemann integral carry over to the Riemann-Stieltjes integral. So for example, the integral of a sum is the sum of the integrals. And if I want to integrate over a region, I can break that region into subregions. And the, in effect, the generalized area under a curve, well, let me say things like this. Suppose that I have an interval. Here's A, and here's B, and here's C. And the theorem would say that the area, or the integral, from A to C is the area from A to B plus the area from B to C. All of these kinds of things can be proved by working with the definition exactly the way they're proved for ordinary Riemann integrals. Things like the integral of C times some function. C is a constant. The constant comes outside the integral sign. Things like that. So everything that you would do with ordinary integrals, you can do with Riemann-Stieltjes integrals. Okay, now we have some other particular results which I want to state. I think I'll do it here. All right, so this is statement number 1 on page 193. It says that suppose, of course there are some other conditions about continuity and all that kind of stuff, but suppose that h prime of x is the derivative of h. In other words, we suppose that the function with respect to which we're integrating is differentiable, and we'll call its derivative h prime. Okay, then it turns out that the integral, the Riemann-Stieltjes integral from a to b of g with respect to h is equal to the ordinary Riemann integral of g times h prime dx. So one way that I can evaluate a Riemann-Stieltjes integral is if the function with respect to which I'm integrating happens to be differentiable, then I can differentiate it, and then the answer is given by this, which has reduced it to an ordinary Riemann integral. And actually the notation suggests that, okay, because I can write this way. Of course, mathematicians shudder when you do something like this, but I could simply say, wait a minute, why don't I simply multiply and divide by dx? And then if I do that, this part here is in fact a derivative. Of course, you can't multiply and divide by dx. Dx is not an algebraic quantity. But if you were to prove this thing, essentially what you would have here you would have a delta x. And the delta x's would cancel, and that's how it would all work out. Okay, then you take the limit, and the delta x goes to 0. Okay, so that's one major property. Okay, now here's another property. And with these two properties, in effect, I can evaluate everything. Okay, now the second property says, suppose, I'll just draw a picture of it. Suppose that my function, let's see, suppose that my h looks like this. Okay, suppose that I happen to have my h is a step function. So let's say it looks sort of like this. There's a value, and then at C1, it jumps. And then at C2, it jumps, and so on. Okay, so how would I figure out the, let's say that, okay, this is x going this way. This is h of x. And I want to integrate this from a to b. Let's say. Okay, so the integral of a step function from a to b of any function g, so I should say it this way, the integral of any function g integrated with respect to h, if h is a step function, has a very simple solution. Because what the answer is, it says, well, remember what the definition says. The definition says that what I'm going to do, here's the way I'll prove this, in fact. I'm going to simply break this down into the integral over each of these pieces between the jumps. Now, between the jumps, the function h is differentiable. In fact, has a value 0. So the change, this is the dh of x, is the change in x as I move along. As long as I'm in an area where h is constant, then the dh of x is 0. So that means that all of the contributions to this integral are 0, except at the place where there's a discontinuity. At the discontinuity, h of x actually changes, and the amount it changes is the amount of the jump. So what that means is that if there were altogether n jumps, then what I would do is I would take the value of g at each of the jumps. Okay, that's this. So I take the value of g at the jump multiplied by the amount of the jump. I'll call that delta h sub k. Okay, that's what this is. That's my delta h. And then I just add those up over how many of them there are. Okay, because remember that if you look back at the definition, what the definition of the Riemann integral is it says, imagine that this x moves from left to right, moves between a and b, and as it moves an infinite number of these infinitesimal steps, then what I'm going to do is I'm going to continually take the value of this function g at each x and multiply it by the amount by which h changes as I move. Of course, if the function h is continuous, then the amount by which it changes is 0 in a little interval as I go through a point. That's the essence of calculus. But if I add up an infinite number of these infinitesimal pieces, then I get an answer. Now, if the h is constant, except for these discontinuities, then over those places where it's constant, the function does not change. And so the contribution from the dh of x is 0. So the only place where this integral is going to have non-zero contributions is where the jumps occur. And when the jumps occur, then at that point, this says take the value of g at that x. Okay, that's where the jump is. And multiply that by the amount of the change as I go through that point. And if it's a discontinuity, then the amount of the change as I go through that point is a positive amount. It's the amount of the jump. Okay, so now for our purposes, all the functions we'll be looking at happen to have the property. They're distribution functions, because that's why we're doing this. So distribution functions are functions that range between 0 and 1. And what happens is, for our purposes, either they're differentiable or they're not. They have some kind of discontinuity. Okay, so what that means is we simply break things down just as we would before, and within those regions where it's differentiable, we replace the distribution function by the density function, by its derivative, and we have the same problem we had before. And at the jumps, at the discontinuities, we simply add in the amount contributed by the discontinuity, which is the value at the jump times the amount of the jump. The value of this function at the jump times the amount of the jump. Okay, so for our purposes, all the Riemann-Stieltjes integrals that we have will be evaluated by reducing them to either sums or ordinary Riemann integrals. Okay, so that's all there is to it. Okay, for example, let's go back to the last homework problem. The last homework problem, you had R, which was defined as W plus X, where X was distributed as an exponential. So X was exponential with some parameter. I don't care what it was. It was a service time, right? So let's say exponential with rate mu. And W had this distribution function. The distribution function of W evaluated at t was equal to 0 if t is negative, and 1 minus c of SA e to the minus 1 minus rho S mu t for t not negative. So if you draw the picture of the distribution function of W, it looks like this. Here's t, and here is the distribution function of W at t. And it's 0 for t negative. And then as you cross through the origin, the function has a discontinuity, and it jumps by an amount equal to 1 minus c of SA. If that's the value 1, then the graph looks like this. So this is a distribution function of a random variable that is neither discrete nor continuous. It's not discrete because it takes values in a continuum for positive values of this index. And, but it's not continuous because the derivative does not exist at the origin. Now, if I look at the ordinary exponential, here's the ordinary exponential. Okay, so now I'm going to plot the distribution function of x. Well, the distribution function of x, if x is exponential, was 0 for t negative and 1 minus e to the minus mu t for t not negative. So it looks like this. Okay, it's basically the same. It has a discontinuity, excuse me, it has, its derivative does not exist at the origin, but it's not discontinuous at the origin. So what that means for all practical purposes is that I can ignore the fact that the density function does not exist at the origin here, because if I go back to the definition of the Riemann-Stieltjes integral, what happens is that the amount of the jump at discontinuity is 0. So it's discontinuous. It doesn't, there is no derivative there. But when I take the value of the function, one function here, and multiply it by the amount of the jump is 0. So therefore, by ignoring it, I don't make a mistake. In other words, let me go back over here. What you're asked to do in that problem is to evaluate the distribution function of R. And there were two ways to do it. I said, OK, one way is to say that f sub r of t is equal to the integral of, OK, now what I'll do is I'll fix the value of x. So you write d f x of u. And then you multiply that by the probability that w is less than u. So that would be the distribution function of r evaluated at t minus u. And then you integrate that over all u. In fact, in principle, it's between minus and plus infinity, except that when u is negative or greater than t, then some of the functions involved are 0. OK, so that was the same thing as the integral from 0 to t of, well, I won't write that out. Let me just say that for our purposes, for our particular example, that piece was 0, and this piece was t. Okay, but if I wanted to be rigorous about it, I would have to first write it between minus and plus infinity, and then by plugging in the definitions of these functions, show that at least one of them is 0 if u is less than 0 or greater than t. Okay, now the other way to do it was to take the same integral, except that instead of putting the r here and the x here, is reverse them. So this would give me d f r of u f x of t minus u. Okay, what I said to do was to do it this way, because if I simply replaced that by the density function du, I would get the right answer. Okay, what I'm doing is what you do in ordinary undergraduate probability, which is you neglect the fact that this derivative doesn't exist here. You say, well, it's only at one point, so what, who cares? Don't even think about it. And you simply went through this arithmetic and you got an answer. And then the homework problem asked you to compare that answer with what the simulation gives. Of course, everybody got agreement, so that indicates that what you're doing is correct. Okay, but suppose I had asked you to do it this way. To do it that way, if you had ignored the jump at the origin, you would get the wrong answer. Because what you would have not added in was you would not have added in an amount equal to, well, let's see. If I did it this way, this is not r, by the way. I shouldn't have put r here. I should have put w. Okay. So erase everything in your mind I just said. Okay, now, if I had neglected to jump at the origin and just taken the derivative of this part, which is what an undergraduate would do, then my answer would be off by the amount of this jump multiplied by this function when at 0. Okay, so the question now is, this is the next homework problem. The next homework problem is to take the previous homework problem. I'll pass it out in a moment, except now, instead of evaluating it this way, evaluate it this way. Of course, you don't have to run the simulation or do any numerical calculations, because we already know what the answer is. All you have to do is show by evaluating this and properly using the theorems about the Riemann-Stieltjes integration to show algebraically that when you get all done, taking into account the correction by adding, that is, adding in the effect of this jump, you algebraically get the same answer here that you got here. So this would just be a dumb exercise in convincing yourself that this Riemann-Stieltjes stuff works. And you don't want to be in the position where if you have problems in which you've got random variables whose distribution function has a discontinuity, that you can only solve them if you happen to formulate it a certain way and not the other way. Okay, so let me pass out this homework problem. Now there's another piece to it which we haven't gotten yet, and I'll get to that next time. I'll start it now. But basically this says, although it doesn't refer to the previous homework problem, it says to do exactly what I just told you to do. And in part A, it asks you to calculate this. Of course, you don't have to calculate this. You've already done it, so you can just copy it over. Okay, so let me pass these around. All right, so this is a simple algebra problem, really. Thank you. So part A asks you to calculate the integral that is this one. Part B asks you to calculate this one and show that the two are the same. Now you notice that at the beginning I defined the distribution function for x and y, and when I talked about the Erlang C, I used an M here instead of an S. And the reason for that is because of the next part of the problem in which there's another S, and I didn't want to get the two S's mixed up. So since this is an integer, it's much nicer to represent it by M or N or something like that, and keep the S as the variable for the next piece, which is now what I'm going to talk about. Okay, so now I'm up to the Laplace transforms, which start on page 197. And probably everybody is familiar already with Laplace transforms. Well, Laplace transforms are to Laplace transforms as Riemann integrals are to Riemann integrals. And by the way, if you're a physics major, or maybe a double E major, but certainly a physics major, you already know all this stuff, although you might have used different terminology. Like, for example, instead of Riemann integration, people use things called delta functions, which really aren't functions. Mathematicians tend not to like it. Okay, so now let me define the Laplace transform. And I'll spend some time on this because this turns out to be the key tool that represents the step from elementary queuing theory to middle queuing theory. So we have the Laplace transform. And the idea is that suppose I have some random variable that has a distribution function f. Then I can define the following if I want. I can take the differential of that, multiply by e to the minus st, and integrate that between 0 and infinity. Actually, between 0 minus infinity. That is, I want to make sure I get the origin in part of the integral. So I'll emphasize that at least at first by writing a minus sign here. Now, if I did that, if you tell me a distribution function, and so I can actually get this arithmetic, multiplied by e to the minus st, and evaluate it, I'm going to get an answer that's going to be a function of this s. That's the so-called dummy variable. And this is a transform, because what this does is it takes some function of one variable and turns it uniquely into some other function of another variable. And you can say, well, so what? Who cares? Why? And the answer is, well, it'll turn out to be very convenient because it's often easier to work with the transformed function than it is to work with the original. Of course, in order for that to be true, you must have the property that if, obviously, if I give you an f, if it exists, you can calculate the phi. But that doesn't necessarily mean that given a phi, you can find a unique f that it comes from. But the theory of transforms says that under certain conditions, you do have that uniqueness. So in order for this thing to be useful, it must be, there must be a one-to-one relationship between the function and its transform. And the second is that there must be some advantage of working in transform space as opposed to working originally in the original space. OK, one last thing before we quit, and then I'll start here next time. And that is that, in fact, from a technical point of view, you could argue that this is the same thing as the expected value of the function e to the minus sx. Okay, if I have a random variable x, and I form a function by making that the exponent of e to the minus sx, so that that's a random function, then the expected value of this new random variable is equal to the values that the new random variable takes times the probability it takes them added up over all possible values. So technically, this transform is an expected value. That'll turn out to be useful as a useful property. OK, we'll start from there next time.